This video is going to illustrate two questions involving Dalton's law. And Dalton just says that the pressure of the individual gases, regardless of what the gases are, their molecular weights, etc., if you know the individual pressures, then they add up to the total. So if the first gas, let's say, is let's say you have some helium and you have some oxygen in a container and you have some, let's say, nitrogen in a container, if you know the pressures of the individual gases, all right, then you will know the total pressure. And this makes sense because you can basically do nRT over V for each of them and just add them up, right? So a classic question that we can solve using this is a situation in which we're given a vessel of a known volume. So we say we have a 2.00 liter vessel, and we're given a temperature of 298 Kelvin, and we're given masses of some gases. So let's say we have 4.0 grams of neon, we have 8.00 grams of oxygen, and we have 14.0 grams of nitrogen. Now, there's lots of ways of handling this. The point is you're trying to make this go as fast and easy as possible, because you can do some really complex calculations or you can find some really neat, easy shortcuts. So if they're asking you for the total pressure and the partial pressure, so they want you to figure out this, and this. Given this information, you could do PivNert 3 times and add them all together. That'll work. I think the easier way is to think in terms of mole fractions, and that's really the way you want to go with this type of problem, right? So what we're going to do is we're going to figure out P total. And then we're going to figure out what fraction of that pressure is caused by each of the individual gases. So I'm going to quickly determine how many moles I have. Now, real quick, the formula mass of neon is 4 grams. So if you divide this by 4, you have basically 1 mole of neon. The formula mass for O2 is 32. So you basically have 0.25 mole of oxygen. I'm dispensing with sig figs here, by the way. And the formula mass of nitrogen is 28. So you basically have 0.5 moles of N2. So I'm going to add those 3 numbers together. I'm going to plug them into PivNert, right? And I'm going to figure out what the total pressure is. So I'm going to put P equals 1.75 moles. Doesn't matter what gas is it. That's the idea of the ideal gas law. You know, every molecule is the same according to the ideal gas law. This we're going to find is not true, but when we're using PivNert, we're drawing on the assumptions that this ideal gas law is valid under the conditions that we've been given. So we have our N, we have our R, which is 0.08206 liters times atmospheres mole K, and then we have our T, which is 298 Kelvin, and we put that over the total volume of 2.00 liters. And when I calculate that out, I get a value of 21.4 liters. I'm sorry, that was a bad thing. 24.4 atmospheres. Sorry, because the moles cancel, the kelvins cancel, the liters cancel, and the only thing left is atmospheres. All right. So what is the partial pressure of these gases? Well, you can think of it as a simple fraction. Of the 1.75 moles, which is like a number of molecules, right? 0.25 of them are oxygen, one of them is Ne. So you can do like this, right? You can go 1 mole of Ne over 1.75 mole of particles, whatever they are, or molecules, right? And basically just multiply that times 21.4 atmospheres. And that will tell you what fraction of the pressure is caused by the neon. So you get the number of 12.2. You can do the same thing with the oxygen, right? So in that case, you're going to multiply it by 0.25 over 1.75. And that's going to give you about 3.06. And then you can also multiply it by 0.5 over 1.25, and that's going to give you the pressure caused by the third gas, which is the nitrogen, and I'm sorry, that's 1.75. Don't want to make a mistake there. And that gives you 6.11. And what you want to notice is these 3 numbers add up to the total pressure in the container. So you want to be kind of loose about using these formulas and be smart about using them. I mean, you could do PivNert 3 times, but it's probably actually more work. And if you understand what's going on here, this whole mole fraction concept, it just means of the moles in there, or of the molecules in there, what fraction of them are oxygen molecules? Because they're going to be causing that fraction of the pressure. The second type of problem that you're going to encounter is the we've got two chambers and we've got a valve between them. This is our chamber 1 over here, and this is our chamber 2, right? And we've got this little valve between them. We're going to open the valve and we're going to let those molecules diffuse. And they're going to evenly mix and form a homogeneous mixture. So the oxygen molecules, which are all on the left over here, some of them will end up on the right, and some of the helium molecules are going to end up on the left. And what will be the final and partial pressures for the gases when we put them in there? Now, you can't just average the numbers, okay? You have the following choices. You can do this the hard way, okay? And the hard way is you find out, okay, in chamber 1, okay, you figure out how many moles of oxygen were in the first chamber. Okay, so that's right. And you do the same thing for chamber 2. You figure out how many moles of gas were in the second chamber. Then you add those two numbers of moles together according to Dalton's law, and then take this n and then you piv-nert the whole darn thing again, and that will give you the total pressure, and this will give you P total. All right. In this one we're going to use the total volume, so we have to change that and make that a total volume, which would be in this case 5.0 liters. So you'll be able to figure out what the total pressure in the 5-liter container is, and then you can do the mole fraction thing again, or you can piv-nert it again using 5 liters. That's a really long, hard way of handling the question. There's a much easier way of handling this question, and it's applying Boyle's law. Assuming each gas is sort of behaving independently, we can assume that, like for example, we originally had we're going to use P1 V1 equals P2 V2, and we're going to do this for each of the individual gases. So ignoring the fact that they're both in there together, let's just act as if the helium is spreading out. So if the helium were to enter the other chamber and mix and now be in a container with a total volume of 5 liters instead of a 1 liter container, what would its new pressure be? So on the left hand side, we had the original 7.00 atmospheres, and the volume was a 1 liter container, right? So on the other side now we don't know what P2 is, but we do know what the volume of the total container is now. So our container is now 5 liters because it's the total space. Because once you remove the valve, the helium's free to go wherever the heck it pleases. And so we can solve for the pressure that the helium will cause based on the number of molecules of helium in that chamber at that temperature. So we can solve for P2 here. And that really is going to be equal to the pressure caused by the helium when the valve is opened up. And when we do that, we get 1.4 atmospheres. We can do the same thing for the oxygen. The oxygen originally was at a pressure of 4.00 atm, and it was originally in a 4.00 liter container. And now it's going to spread out and fill up that whole extra liter, so it's 5.00 liters. And we got to find out what our P2 is, which is really equal to the that's really the pressure of the oxygen when it's spread out in the whole container. When we do this, we get the P2 is equal to 1.4. I'm sorry, no, it's 3.2 atmospheres. Now this gives you the partial pressure. So here we have the pressure of the helium, and here we have the pressure of the oxygen. And if we want to know what the total pressure in the container is, we can just add those two numbers together, and we will get a total pressure of 4.6 atms. Again, not focusing on sig figs here or even getting the right formula masses for stuff along the way. But it's a much easier way. Basically use Boyle's law twice, and you can get the individual pressures and just add them up that way. Just throws you because it's like, well, don't they interact? Yeah, they do, but really it's how many molecules are banging against the walls of a bigger container. And that's all.